should be close to the microphone. Hello, everybody. This talk is a little bit different. Here on the slide, the talk title is also slightly changed. So, how to kill the language with incremental improvements. It's not trying to be a tutorial. So, but before I get into that, just a little bit of advertisement. Roughly at the beginning of next year, we are starting a new project, hopefully, if everything goes all right with EPSOC. They seem to be very slow these days. But if you are into Go, Erlang, formalization, formal verification, and C hacking, talk to me. So we are hiring a postdoc specifically. Okay, so as I said, the title is slightly changed from what's on the internet. I think that microphone is open. I hope I can take questions throughout the talk if you feel like it, because the internet felt like shouting at me for the abstract that probably got you here, as incredibly lazy and anti-intellectual framing, probably about the things I might be saying about Python. Another more generous title could be perhaps asking the Python community, can we help? Okay, so to get a bit of a feeling, show of hands, who is using actively more or less Python? All right, okay, good. About half, I would say. So you might have noticed a little bit of change in Python over the last 4 release cycles. There are 2 companies that have been pushing really hard on changing Python, how it works, specifically Microsoft and Meta. And one of the most notable, here a little bit older, I think the latest release is Python 3.14, and they are even faster. That's purely the interpreter. So we see here about a 2x change from the version 3.9. So that's quite an achievement in terms of interpreter length. Python was known to be really slow. Now it's just slow, not really slow anymore. But yeah, so that's here on micro benchmarks. That work is kind of driven, or was driven, by Microsoft. They spent a lot of engineering to make that happen. There was a Faster CPython team. They changed the interpreter in major ways, and I will talk about some of the details here. They also introduced a just-in-time compiler, not very successful yet, because it's not quite as fast as the interpreter on many systems. But yeah, I think originally it was kind of motivated because they run their Python lambdas that you can use in Excel these days on the cloud. So any saving there is probably good for their bottom line. Okay, but that's only one of the things they have been doing. So there's also the whole story of Python, which really wants shared memory, parallelism, concurrency, because it's a great programming model, as we all know. So, sorry, I don't try to judge. I'm a language implementer. I shouldn't judge. But so at the moment, there are 2 versions of Python. So if you download the latest Python release today, you should have 2 binaries. One of them has a classic global interpreter log. So we have that thing here. And the idea is that in the classic days of Python, you would execute maybe some random Python code and then maybe do some kind of machine learning, because everybody is doing machine learning, I hear. But what actually happens is you run a little bit, and that's a time slice of the left, and then you run a little bit of the right, and then you go over, back, and so forth, and so forth. So you don't really have parallelism. And with what they call free-threaded Python, now you actually have proper parallelism. So I saw somebody, yeah. Yes. The code runs in parallel. Both of your things can do their things at the same time in the same memory space. And all that work is driven by Meta. They are running their code, specifically their Instagram on Python. And so for them, it's really cool to utilize all the new faster interpreter and have also their free threading. Because more threads means you can run more requests on the same machine within the same memory space. So that makes much cheaper to run Instagram. So what could possibly go wrong? Okay, it's supposed to be a rhetoric question. Let's look at the simple example. So this is actual code. This is code from a bug report. I will go about the details a little bit later, but let's read through it a little bit. Half of you know how to read Python. For the other half, that's supposed to be an object typically. So here we read a field. So we get kind of the next ID. We want to use it as a request ID and return that, which is not on the slide. And then we increment just the next ID, right? +1 and assignment. So in Python, with the global interpreter lock, show of hands, do you expect that to be atomic? No, okay? Very few. It's not atomic? Show of hands? Okay, more, yeah. It's a beautiful engineered language, so it's a bit more difficult. Let me rephrase the question. Things changed over time. So, do we assume that in the version 3.9 of Python that was atomic and now it's not atomic anymore? Or basically the other way around, it used not to be atomic, but now it happens to be atomic. So show of hands, it was atomic, but it's not atomic anymore. All right, okay. It wasn't atomic and now it's atomic. Okay, so one eager, one who might have had something to do with it, I don't know. Yeah, before I get to the results of that, let's have a little bit more fun. Many of you have probably been here because you submitted papers via HotCrab, and HotCrab has that extra feature that as share you can enable, and then you get kind of randomized paper IDs. And I looked at some of these paper IDs to guess kind of what it's actually doing. It's not really random. So what I figured is something like, we do a modulo and then some constant possibly, and that's how we get the next. So we have a semi-random increment here. Right? So interestingly, on Python 3.10, 3.11, 3.12, 14, and so on, this one is atomic. So that also answers the previous slide. So it used to not be atomic, and now it is atomic. It's a beautiful language. Okay, but so let's imagine I had somebody collaborating with writing that code, and now I come into the code review and ask, well, what's actually the purpose of this bit? Can we maybe refactor that and give it an explicit name? A reasonable request? Yeah? Yeah? Yeah, okay, good, good. So I'm not the only one. So now we have that code refactored to our snippet from before, and now we call just a function because it's Python, and that's the right thing to do. And yeah, from a software engineering perspective, great. Now we remember why we have that modulo operation there. Great. Now, of course, again the question. But let's not ask the question of what it actually does. Let's ask a question what we think it should be doing, right? So, show of hands. Should this code still be atomic? Okay? No? Okay, so everybody else? I hit Python? Yeah? All right, yeah. Obviously, what happens is now it's not atomic anymore, because otherwise there wouldn't be a talk. So why is it not atomic anymore? The technical details for all that is how the interpreter is implemented, and I don't have a specific slide for that. But so basically, the interpreter used to check for the global interpreter lock at every single bytecode, basically, more or less. And now it's really just checking for the global interpreter lock at function calls and at back edges of loops, which is a classic thing compiler people do, because that's how you get performance, and then you get these kind of interesting effects on your language, where things were atomic, or no, they were not atomic, and now suddenly they're atomic, but then if you refactor your code, where refactoring is supposed to not change the semantics of your code, then suddenly you introduce a new synchronization point. Okay, so what does the specification say about all that? Well, there isn't one. So you go to the people who came up with Python, and then you ask. And so I had a brief exchange of 2-3 emails with Guido, and the official answer is basically, we never promised anything, and you should really be using logs. And that comes from the perspective of, indeed, a language implementer, a language designer, and we want to be free to change things underneath, right? Which is, unfortunately, I think, a little bit problematic because people program against real systems. They test on real systems. They run their production software on real systems. They observe software on real systems. And then suddenly you change the semantics of a real system, and yeah, I think that could be problematic. And yeah, so just to give credit where credit is due, that snippet of code in its original form, here slightly changed on the slides, comes from a bug report against PyPy. So the code ran fine on CPython, and then somebody went and ran it on PyPy, because PyPy is a nice just-in-time compiler for Python, gives you quite a bit of a speed boost. Of course, it's a different implementation, and things work slightly different there. And there they observed race conditions, which they did not observe on CPython before. So it's not a made-up thing. It's something that happened to people actually in production, because nobody knows that you have to put a lock around it. Because the global interpreter lock most of the time protects you, but not always. Okay, so where did I want to go from here? Right, so just to emphasize, in 3.9 Python, we had a global interpreter lock that was basically checked on every single bytecode. That means you had a bit of a chance to observe your non-determinism. Okay, there is some mismatch here. Okay. The release of the global interpreter lock is unfortunately time-based, so it's not very predictable. On the other hand, if you really have an application that runs on 3.9, you can reduce the time interval at which these locks are checked to make it more likely that you actually see your concurrency bugs, so that you don't just see them in production every millionth request or something like that. So you can make it slightly more predictable. So now, with all the beautiful performance changes to Python, we are in a situation where the bytecodes got changed, and we only check for the global interpreter lock at function calls and back edges. So that means this bit of code here, assuming there are no kind of meta calls and all the beautiful things you can do in Python, this will run straight in atomic, and you will never see any thread kind of writing to next ID, updating it in between you returning and whatnot. So that's nice and atomic. But then, of course, if you refactor it, suddenly you introduce a synchronization point and you can actually see the races. Why is that a problem, you might ask? Well, if you look from it from the perspective of evolving a language, then we are in the situation where Python 3.9 is slow, but you have some chance of noticing a concurrency bug. From 3.10 on, you're a bit faster, but you have no way of seeing your bugs anymore. And then with 3.13, since you have the free threading, then you either have no chance of seeing your concurrency bug, or suddenly on the free-threaded version, everything is your concurrency bug, right? Because of course our code on the free-threaded version doesn't make any sense at all, and indeed you have to put a lock around it. So what does it mean for an ecosystem? Yeah.
So in your example with the factorized version, which has the function, right? The reason is the return statement still atomic, the return?
So the problem with the version with the function is that the function call itself is one of the bytecodes that will check for the global interpreter lock. And if there's another thread that wants that lock, then it will release it, right? So at the boundary of the function call, you will get descheduled, the other thread gets its turn, and then before you had a chance to update your request ID, somebody else may have updated it already. And
That's
then,
why it's not atomic.
yeah, exactly. Yeah. Okay, time-wise, how am I? Yeah, should be fine. So, on a previous talk in this room, I think we saw kind of the no, that was another room. We saw the classic kind of synchronization situation. You have an object, and you want to communicate whether you have to continue going in a loop, right? So here in that thread, we assume that's the right-hand thread. We run in a loop, we check that object field, we read it. And then over here, we have another thread that does something, maybe just sleeping, but sets our keep looping flag to false so that that one can continue. One of the big questions here is, what would we want that to do? Does anybody have an opinion on that? Should that work like it works in, well, I can't think a language where it works. So the point I'm trying to make here is most languages have a pretty low level, but these days somewhat understood memory model. And you would want to have some specific semantics of when that write and read, or read and write, is actually synchronizing. Now, there are people that implement Python on top of the JVM, so they inherit the JVM memory model, and in that case, this is just an object read and nothing special, and that one gets moved out of the loop. So if you have an optimizing compiler, then suddenly your program is not synchronizing anymore. So you have a classic kind of empty loop deadlocking here, and that thread will never make process again. So my point being is, Python, especially if some people invest in optimizing compilers, needs something like a memory model. Yeah. So specifically, if you have heard of GraalPy or GraalPython these days, that doesn't work. So that actually gets stuck. Okay, so if you have a high language like Python, we may want a memory model, maybe something inspired by C++ or Java, but maybe we want something that also takes kind of explicit inspiration and in the needs of what people consider Pythonic, right? So there are billions of lines of code out there that you may want to support, and then people do interesting things. Let's imagine, because dictionaries are so easy to use, we could use a field, of course, to synchronize, but we could also use a dictionary. And maybe there is something in the dictionary, and then one thread. Here it's a synchronization loop, just to make it simple, as with the previous example. Maybe we check whether there is that element in the dictionary, and here over we might remove it from the dictionary, right? So you have all these things. You have lists that are changing sizes all the time because they are just appendable lists. You don't have a fixed array data structure in the base language without the extensions and so on. Yeah, so you may want a memory model that does not just consider basic reads and writes to memory, but considers the built-in data structures of the language as basic primitives that have specific meaning in the context of concurrency as well. And then, of course, you run into all these kind of issues with parallelism and concurrency, make it scale, make it kind of fast, make it not break everything that exists. So yeah, there are a whole host of requirements we could put up. I'm not going to go into detail, but one of the challenges of languages like Python or Ruby or most of the dynamic languages out there, they have objects where you add fields, remove fields, very much like the dictionary we just saw. And you have to make all that work, and you have to kind of design a memory model that accounts for these opportunities and possibilities in the language, because people actually use them. So, given the time, I'm not going to go into loads of details. I'm just trying to hand-wave my way through. We did some work in the past, which I think could be part of a solution to such a memory model. The basic idea is that you can kind of split up your heap into objects that are local to a thread and never reachable by others, and then objects that are reachable here in blue by other threads. And you really only need to synchronize on those, and you can keep the performance for those really as quick as in your single-threaded Python. And we did that with object shapes, and we did some more work to do that with also with collections, so arrays or lists in the case of Python. And yeah, we have some ideas of how to make that work. It's all about avoiding the extra synchronization if you don't need it. But as I said, I'm not going to go through the details here. Yeah. Wait, where are we? Here. Somehow those two screens don't synchronize. Right, so part of the story at the beginning was that Microsoft was one of the big companies throwing money at the Python ecosystem, had actually a nice team to make Python faster, and then they laid them off. So in some ways, colleagues tell me that kind of solves the issue, because nobody works on Python performance anymore. I'm not sure that's true. There are loads of people in the machine learning community interested in Python, so I'm sure they continue to invest in Python and Python performance. I just yesterday saw a blog post where people did inference in parallel in multiple threads now, because you can do it with three-threaded Python. So if people actually invest into the future of Python, we will need a memory model. And I think that will take quite a lot of research. That will take compiler people, language people like here. I know there are also software engineers around, so it will also need software engineering research, because we don't really know what Python code looks like with respect to concurrency. They have been doing loads of asynchronous stuff for, I think, a decade or so. Yeah, so what do we actually need in terms of a memory model? What do Python programmers even expect? Because the normal Python programmer doesn't really think about parallelism. They may still know the global interpreter lock. So yeah, what's the right thing? What's the right language design for such a language? So for me, the call for action here is, please talk to me if you want to follow down that rabbit hole. I think it's a really deep one. There's lots of work to be done. But I think we have some ideas of how to get started. And then, last but not least, I'm looking for a postdoc, so come and talk to me. All right, thank you very much.
Actually, we have 6 minutes for questions.
If you could return to the spin weighting slide.
Yeah, give me a second.
The one before this. Yeah, yes, there we go. Yes, while object.keep looping. So you mentioned that this has to do with memory models, and for me that's a very unusual way of describing this. I come from the Haskell world, and what you have here is basically an effectful value. Now, what you could do is basically, rather than treat that as basically like some constant as part of the object, you can fix it by making it a function call, so that every time, you know, this is actually a function, and you're going to keep calling the function, because it could be different. Right.
Right. You could do interesting things, right?
Because
so
the point is to not prevent it from being lifted out of it, and so that's not really that to me has nothing to do with a memory model. This really has to do about optimizations, and the fact that this optimization doesn't apply because you don't have a static value, you have an effective value.
So. From my perspective, I think there are two things to that discussion. And one is perhaps the way Python people program. Mm-hmm. And they're used to write that type of code, right? So you have a shared object that's simply a field. Mm-hmm. Yes. So what's now the right way of communicating to the Python people what the right way of doing is? Maybe indeed the right way is to say, the only way you get synchronization semantics is with some kind of function call, or in Python maybe it's a property, and then you have getters and setters behind that, and whatnot. Or maybe you go the Java route and you say that field's supposed to be volatile.
Yes, there you go.
Right.
Yes.
What
values mean?
To define
right,
what these things mean, right, in memory model. One thing you definitely don't want is that every single field write and read has basically volatile Java semantics.
Oh
right?
no, that would be very inefficient. Yeah.
Exactly, right. So it's not so much is that the right way of programming? For me, as somebody who sees that language being used, it's more a question of what should we do? What's the right way to kind of get the community along to support the existing code bases and find a solution that kind of evolves the ecosystem instead of kind of crash and burn.
So notice that when you're sort of like trying to solidify the memory model, you're basically walking slowly to basically a type system, because it's like the volatile keyword is basically a type annotation to variables.
That's certainly one possible option, yeah. But then if you say types, then you have at least 75% of the Python community tell you, over my dead body. Right? So there's a lot of social, not just technical aspect to it. Yeah.
So we're encountering a similar version of this problem in the OCaml world, where we got a nice new runtime capability of a multi-core runtime without a suitable programming model. And now the work we're doing at Jane Street with this kind of OxCaml branch is building in data race freedom at the type level. And just like the main observation I have from this is like, it has taught us that the data races are much subtler than we would have expected. Like as we try and propagate the type information through, which itself is like a lot of work, you discover the data races that you didn't think were there because they're like sneakily hidden all over the place. Obviously in the Python world, you don't have the option of, no one is going to accept, 33 different like modes for tracking data races stuff. So assuming that you are in a world where you're doing mostly dynamic solutions, do you have any thoughts about what you do in order to discover and fix the data races in the enormous corpus of Python programs out there?
Talk to the software engineering people, that's my approach. I think we have to develop tools to look into these things. But maybe to not answer your question, but point at some other work. Tobias Rikstedt from Stockholm, Uppsala is not in the room, but we have been talking loads about these things. And he is in contact with the Python community to kind of propose a programming model, a new programming model, kind of they call it cones, where you kind of delimit which kind of part of the heap you can access. It's a different way of modeling things. A bit like actors, not really like actors, something that fits more into that kind of world. So I think we should probably, as researchers, pursue multiple avenues, propose to them possibly programming models that kind of fit into their language and steer them a little bit to that data race-free kind of design and having neat language mechanisms to enable them to do more powerful things. But yeah, it's always a question of how accepted that's going to be in the community. The Ruby community, they have their reactors, which nobody uses. And yeah, so, but indeed, I think to take along as much as possible from the community, we need to have tools to find data races. Yeah, absolutely.
Great. Let's thank the speaker again.